Welcome to another episode of How the Body Works, an educational series as a part of McMaster's Demystifying Medicine. I'm Matt.
And I'm Susie.
And today we'll be talking about the chemistry of the body. Let's talk about the chemistry.
Did you know that an average person takes about 12 to 16 breaths per minute? I didn't think so. Many people don't realize the important role breathing plays in our internal environment. But in order to understand this role, we'll have to look at some of the physical and chemical reactions that govern major functions of our body. Let's start off with 3 basic laws.
First, there's the law of conservation of mass, which states that the total mass of the reactants must equal to the total mass of the products after the reaction. In short, mass doesn't magically increase or decrease in the reaction, it remains the same. Second, there's the law of electrical neutrality, which states that the sum of the positive charges must equal to the sum of the negative charges in a neutral solution, like that in water. Third, there's the law of mass action, which governs the ratio between the reactants and products, thereby helping us predict the outcome of the reaction. For example, both water and hydrogen peroxide are made from hydrogen and oxygen. However, one is required for our survival, while the other may be used to kill us. How do we make one and not the other?
Next, let's talk about water. In order to discuss the significance of water in the process of homeostasis, we first need to consider its dissociation properties. We are all aware that water exists in a very tight conformation due to the phenomenon of hydrogen bonding. However, water has a very unique ability to act as an acid and also as a base depending upon whether it accepts a proton or not. This reversible process is only seen in the presence of 2 molecules, and this is known as autoionization of water, meaning that water dissociates or ionizes into equal concentrations of hydrogen ions and hydroxide ions. Additionally, pure water is different from the normal tap water. How, you may ask? It's different because it contains equal amounts of hydrogen and hydroxide ions. Hence, pure water is neutral due to the balance of oppositely charged ions.
Moreover, the dissociation constant of water, Kw, is a very small unitless value, and it represents the product of equal concentrations of hydrogen and hydroxide ions. Any change in one of these ions results in an inverse effect on the concentration of the other ion. In order to deal with the messy math involved, the concept of pH was created to measure the acidity of the solution. Ever wondered what that P stands for? Well, it stands for the negative log of the concentration of hydronium ions. So if the concentration of these ions is 10 to the negative 7, then the pH will be 7. Consequently, an increase in the concentration of hydronium ions will indicate a low pH and vice versa. Phew! After all of this, I think I deserve a glass of water.
In chemistry, we often come across the phrase strong acids and bases. Simply put, they are defined as chemicals that completely dissociate in water, meaning 100% of its components are broken down to its respective ions. For example, let's talk about hydrochloric acid. Widely known as a strong acid, once placed in water, 100% of the given HCl will dissociate into hydrogen ions, also known as protons, and chloride ions. And the same rule applies to strong bases. With that said, strong acids and bases exist in the body, however only as dissociated ions. If they were to remain in our bodies as undissociated acids or bases, that will lead to serious physiological consequences. A few common ions that exist in our bodies are sodium, potassium, and calcium, which are cations due to their positive charge, and sulfate, carbonate, and chloride, which are anions due to their negative charge. These ions are crucial for proper bodily functions and must constantly be regulated to maintain an optimum concentration.
So the next topic that we'll be talking about is weak acids and bases. A weak acid is essentially what you believe to be the opposite of a strong acid, and a weak base is what you believe to be the opposite of a strong base. A weak acid or base only partially dissociates the solution. Essentially, when these types of acids or bases are added to a mixture, only some of the molecules completely separate into the constituent forms. Now you may be wondering, how does this impact the human body? Weak acids and bases have the ability to create buffers, which are solutions that are able to resist changes in pH when an acid or base is added. This is very important in the human body, where consistency is essential.
Now, just for the sake of interest, I want to talk about 3 groups of weak acids that are important in blood. We have blood plasma proteins made up of amino acids known as the building blocks of our body. We also have hemoglobin, which is another component of our blood used to carry oxygen. It is composed of protein molecules, which are also weak acids. Lastly, we have phosphates, which are essential for our metabolism. Believe it or not, that's not all. Amino acids can act as either acids or bases depending on their type and their environment in order to maintain pH. This is because they have an amino group and carboxylic acid group, which act as a weak base and acid respectively. If the environment is acidic, the amino group can absorb hydrogen ions. On the other hand, if the environment is basic, the carboxylic acid group can give off a hydrogen ion.
Well, that's all we have for today, folks. Thank you guys for listening, and we hope you enjoyed today's episode of How the Body Works. Next time, we'll be covering carbon dioxide and the influence of breathing on the hydrogen ion concentration in the body. Please click, follow, or subscribe. See you guys next time.